dump this video on my computer and then start over. Okay, so this is the point, right? Taylor's theorem, this isn't even what Taylor's theorem says. Taylor's theorem is telling you how good the approximation is. But if I just say, give me an approximation, oh, you just take the Taylor polynomial and you've got it. So we just have to plug in 0.3 into that quadratic polynomial there. So it's just 1 plus half of 0.3 minus 1/8 of 0.3 squared. And you don't need to worry about what that actually comes out to. It's about 1.13875. 13875. Okay. Well, actually, this is equal. Okay. So that's an estimate for the square root of 1.3. The more interesting question really is, well, how good is the estimate? So that's the final part. Part C is given upper bound. Part C says given upper bound on the error. We're trying to find an upper bound on how much could that error be. And again, we're not going to find out what that error is by actually evaluating the square root of 1.3. We can't do that. We're imagining that that's not something we are able to do. We just want to use the Taylor theorem. So how am I going to find an upper bound on this error? Yeah, I've got to use the remainder, right? The remainder is actually, this quantity right here is actually the exact error, right? Because this remainder is literally f of x minus p2 of x. This is the exact error. The only thing is we don't know what c is, so we can't find the exact error. We can only get an estimate for it, right? So what we want to do really is get a worst case scenario on what this could equal. So I have to figure out, let's see, what would make this the biggest that it could be? The 6 is a constant, so we're not going to mess with that. But in terms of everything else we see here, how am I going to get the biggest number out of this? And by the way, we already know what x is. X is 0.3, right? Because we evaluated f of 0.3 by using p2 of 0.3. So we are obligated to put in 0.3 for this x as well, right? So the issue is the c, right? Now c is between 0 and x. So in other words, c is between 0 and 0.3. Right? And I'm looking at this is my third derivative, right? And I want to make this as big as possible because I want to get the worst case error, right? I want to know what's the worst possible error. So if I want to make this as big as possible, what should I choose for c? 0, right? I want to make the denominator small. And I make the denominator small by making c equal to 0. That's the smallest that c can be. And that will give me 3/8 when I evaluate it there, right? So the remainder, R2 of 0.3, is at most, I guess it was 3/8 times 6. We've got a 6 on the bottom. And then we've got 0.3 cubed. Okay, so 1 over 16 times 0.3 cubed. And that actually is equal to, not that this matters, but 0.00168875. So it's a small error. But that's the worst the error is. That's not the exact error. If that was the exact error, well, then we could take it and subtract it from whatever we calculated here and find the exact value of radical 1.3. We're not doing that, right? We're just getting an estimate on the error. It might be less than that, but this is the most it could be. Okay. Everybody with me on that? Okay, so that's an example of using Taylor's theorem to estimate the value of something. And there's another one of those, I'm sure, in the review packet for the exam. These make good test questions too because they're computational, and part A might be state the Taylor's theorem, and then part B might be some problem that's based on it. So don't be surprised by that. Be sure that you're able to handle it. Are there any questions on it? Okay. If not, I'm going to jump ahead and do problem 5 next, because problem 5 is more related to the material we were just talking about. And this problem 5 is a really good problem. Here's what it says. You take the function from R to R defined by f of x equals the absolute value of the sine of x. And then here are the questions I'm going to ask you. These are all thumbs up, thumbs down. Okay? F is continuous on R. Second part will be F is uniformly continuous on R. Third part is F is differentiable on R. And the fourth part is F is Riemann integrable on the closed interval 0, 1. So this is a 4-part problem that would probably be worth like 30 points of an exam. Like this would be a big, big thing. And there are some examples for you to practice of this nature also in the review packet. Be sure to look at those. Okay? This is a really... The reason I like this problem is, in addition to all there's so much content covered in these 4 parts of the question. If you understand all of the parts of this problem, you really have understood a huge chunk of midterm 3, what midterm 3 is about, right? For one thing, do we have to just go down the line 1, 2, 3, 4 in order in the way that they're presented here, or are there relationships that we might exploit? So if it's differentiable, then it is what? Continuous, right? So if C was true, then A would have to be true. Any other relationships we know?
If it's uniformly continuous, it's continuous.
Right. If it's uniformly continuous on R, then it's continuous on R. And in certain cases, continuous implies uniformly continuous. Is this one of those cases? What's the main case that we know that a continuous function is also uniformly continuous on the domain?
Closed interval.
Right. If my domain is a closed interval, that's theorem 4.4, then continuity and uniform continuity are equivalent. We don't have a closed interval here. We have the unbounded real line. Okay, so there are relationships here. So we should exploit those a little bit. The other thing we should probably do is get an idea which of these are true first before we launch into just randomly trying to prove things. Because for example, if we believe that it's differentiable, then we should prove that first. Because then we won't have to prove that it's continuous, because that's implied by the theorem. So let's not waste time repeating ourselves. So to help us maybe answer this question, can I draw a graph of it? Let me draw a graph. So this is the sine of x function, so it's positive from 0 to pi. Normally it would dip below the x-axis, but we're making it positive again by taking the absolute value. Same thing over here, it normally would go to the left of the y-axis, it would be negative, but we're taking the absolute value, which makes it positive. So it's kind of some shape like that. Okay. So let's just do a quick thumbs up, thumbs down. Do you think it's continuous? I do. I mean, you can graph it without picking up your pencil. Okay, that's the intuitive reason. Do you think it's uniformly continuous? When you're thinking about uniform continuity, what sort of things do you tend to think about? You have the definition of uniform continuity, which is on the quiz. For all epsilon, there exists a single delta that will work for any pair of points that are within delta apart from each other. So there's the definition. Is there anything else we have? Bounded derivative. Do you think the derivative of this is bounded? Well, what's the derivative of sine of x? Cosine of x. Is that bounded? That is bounded. Of course, this isn't that function. This is the absolute value of the sine of x. But in terms of the steepness of the graph, so even though you've flipped everything positive, right, would you say that there's a maximum steepness to this picture? It doesn't go above?
I guess
There's a lot of
I
hesitation
guess
here.
kind of the way I see it is, like if it was a x squared, you know, like on 0 to 1, it's
Right.
only continuous.
Yeah.
So that's kind of like what I see it as, just like a parabola. Like it's just different parabolas.
Yeah, it's almost like, it is true, the picture just repeats itself. So if something's true on the closed interval 0 to pi, for example, right, then that is just repeated over and over again to the left and the right. So the fact that we really are considering all of the real number line isn't so relevant, because really, when it comes down to the core of these questions, we really are answering them on these intervals of width pi. So what do you think? Do you think it's uniformly continuous? Nathan and Matt say yes, and everybody else is pretty quiet. Okay, let's come back to that. Do you think it's differentiable?
No.
Okay, it's not differentiable. Why not?
No. Math 150A answer, you got points.
A sharp corner, right? Yeah, sharp points, and that means the slope is not defined there, right? So that already is actually problematic with respect to uniform continuity, because this whole bounded derivative thing is a great theorem, but it's a great corollary, I should say, corollary 5.4. But it only works if the function is differentiable. So one of the reasons I asked this question, that I like this question, is I'm forcing you to consider uniform continuity in the absence of that corollary. That corollary cannot be used because the function is not differentiable on the domain. So, so it seems like we have a yes here, and we have a no here. So we're still not sure about uniform continuity. What about Riemann integrability? Do you think, and by the way, 1 is going to be right about here. So we're talking about that right there. Do you think that that's going to be Riemann integrable? I mean, for one thing, you don't even need the absolute value bars, so you're really just integrating sine of x, which we all know that we can do. Okay, so you should be thinking yes on that one for sure. Okay, so we've at least got some headway here. Let's go back to uniform continuity. I'm going to try and convince you that it is uniformly continuous. Okay, but I'm not going to prove it using the corollary, because I can't use the corollary. Let's just focus on the definition. Okay, the intuition is, yes, there's a maximum steepness to this graph, right? So the intuition should be that it is a yes. So if that's our guess, we can at least try it and see. All right, so let's do that. So I'm going to do proof of B, because if that can be proved, if I can prove B, then A will also automatically be true. Okay? So to prove from definition that F is uniformly continuous on R, how do I start? Good. Let epsilon greater than 0 be given, which we've been doing for weeks. Okay. Our job is to come up with a delta, and it's going to be a delta, so we need to find a delta such that if absolute x minus y is less than delta, then absolute f of x minus f of y is less than epsilon. So in other words, we want the absolute value of f of x, that would be absolute sine of x, minus f of y. We want that to be less than epsilon. Does this look familiar? This should look familiar from way back in chapter 2. There was an inequality for that. In other words, if you just take the two functions and subtract them first, that's going to be more than if you make them both positive first and then look at what the difference is. Okay, so this is actually corollary 2.1. Okay, and so now we've got, really our task is now to show that sine of x minus sine of y has an absolute difference less than epsilon, right? It's almost as if we're looking at that function, right? Now if it was just that function, just sine of x, would you tell me that it's uniformly continuous or not? If it's just sine of x. Is sine of x uniformly continuous on R? Yes, why? Sorry, the snapping fingers means it should be quick. What's the derivative of sine of x? Cosine of x. Is that bounded?
Yeah.
Yes. So sine of x has a bounded derivative, so the sine of x is uniformly continuous. Let's use that right off the bat, okay? So since, I'll call it g of x equals sine of x is uniformly continuous on R, there already exists a delta for the g of x function. Okay, so there exists a delta such that if the absolute value of x minus y is less than delta, then the absolute value of g of x minus g of y, we already have a delta that accomplishes this. Because sine of x is uniformly continuous already. But what is this? It's just this. So we're done. This delta that we found right here is the right delta. It does work. Okay? So we haven't used differentiability of f of x at all. We've instead used a slightly different function, which is g of x, sine of x. And we've used the fact that that does have a bounded derivative. It's a really nice problem. This is kind of a clever application of corollary 5.4. Not to the original f of x, but to sort of this parent function of f of x. But that's all we need, because the corollary 2.1 allows us to sort of replace f of x minus f of y with g of x minus g of y, and now I've got a simpler function to which I can apply the bounded derivative property. Okay, so b is a yes, and therefore since uniformly continuous functions are continuous, a is a yes. You see why I like this problem. We're putting a lot of concepts together here. Okay, let's, any questions on that? Let's address the differentiability. We said no on differentiability. Of course, if a function is not differentiable, all we have to do is find one point where it's not differentiable, because it says differentiable on R, and we said no. So can somebody give me a point that might be relatively straightforward to work with?
0.
I would say so. Okay, so 0. That's a sharp corner right there. So basically, we want to try and show that, so for part C, f prime of 0 is what we want to look at. And hopefully it doesn't exist. Of course, the definition of it, which is something that you definitely need to know for the exam, is this limit of this quotient here, right? F of x minus f of 0 over x minus 0. And we would like this to not exist. And this is just the limit as x goes to 0 of absolute sine of x all over x. Okay? So looking at this limit, we would like it to not exist. Can anybody remind me, if I want to convince somebody that a limit does not exist, how do we usually try and do that? Right, sequences. So this comes under the heading of, well, this is something we learned a while back. It's not really pertinent to the material specifically for this exam, but you can't treat this midterm like it's in a vacuum from everything else, right? Obviously we use this corollary here. We're going to use sequences here. There's material you need to know from earlier, but I'm hoping that it's fresh enough that you'll be able to recall it when you need it. Okay? So let's assume, by way of contradiction, that this is equal to some value L. It's not, but let's suppose that it is. What that means is that if I take any sequence of points that converges to 0, the image of that sequence of points has to converge to L by proposition 4.6. Can somebody give me a sequence of points that would converge to 0? Say again? 1 over n is like the easiest possible choice, right? That clearly converges to 0. And incidentally, this midterm is not about convergence of sequences, so if you just simply wrote that down, that would be perfectly fine. Okay, I'm not asking you to prove that right now. Okay, so that converges to 0. Wonderful. So then let's look at the image of that sequence. Oh, it's not, I'm sorry, it's not f of xn that we want to look at. It's actually this whole fraction. So let me just write it out as absolute sine of xn over xn. Let's see, sine of 1 over n is just sine of 1 over n without absolute value bars, because that's going to be positive. And then xn is 1 over n, so it looks like that. Okay, does anybody know what happens to that as n goes to infinity? Blows up. Don't think so, actually. I think I talked about this in an earlier problem session. If you have sine of h over h as h goes to 0, the sine of h actually has a Taylor series that has, h as the first term, and then it minus a bunch of other terms that involve higher powers of h. And of course, in those higher powers, when h goes to 0, that stuff all goes to 0. The only thing that really survives is h over h. So this limit is actually equal to 1. Okay. You can also kind of figure that out from the graph, I guess. The slope of this thing here is 1, right? So if as I go along this way, this is coming down almost along the line y equals x, right there. Okay, so that's a good approximation. Okay, so that's a sequence. Can somebody other than Dom give me another sequence? Negative 1 over n. That would be my best. I mean, after all, the pathological behavior of the function at this point is the nature of it is that you have two directions that are both converging to this point with different slopes. So you should, with your second sequence, actually let me call it y sub n, you should use a different sequence that comes from the other side, right? All right, so then in this case, the absolute sine of yn over yn is, well again, sine of negative 1 over n is the same thing as negative sine of 1 over n, but the minus sign dies when you take the absolute value bars. So it's actually just sine of 1 over n on top again. But this time on the bottom, it's negative 1 over n. So what is that going to converge to? Negative 1. So L has to equal 1 and negative 1, and that is a contradiction. That's a contradiction. Make sense? Okay, super. So it is uniformly continuous and continuous on R, but it is not differentiable on R. Any questions so far? The last part is the Riemann integrability part. And our intuition tells us that it is Riemann integrable. If I want to prove that something is Riemann integrable, what comes to mind as the best or easiest way to prove that? This is where you guys are going to have to kind of put in some overtime work to really get this down, because we really, we've had basically a lecture and a half on it, but it's come pretty recently. So if you're not solid on this stuff, keep watching that 15-minute video for one thing, because that really tried to hit the highlights. but also just really keep going back through those lecture notes again and again, because like I said, we've only got 4 days to kind of get this down. So when I say, how do you prove that something's Riemann integrable, there should be a quick response to that. Which is, anybody want to try me?
For all epsilon greater than 0, there exists a partition belonging to partition space such that u of p of f minus l p of f is less than epsilon.
That's it. It's theorem 6.2, right? So for all epsilon greater than 0, there exists a partition in the partitions of the interval AB such that UPF minus LPF is less than epsilon. That is the correct answer for how do you show that something is Riemann integrable. Now, if I say, what is the value of the integral? This theorem won't do that for you. This theorem only will tell you thumbs up, thumbs down, whether it's Riemann integrable or not. So read the question.